Moving coil galvanometer. Galvanometers could be classified in two types depending on the principles. One is moving magnet, the other is moving coil. Now, a moving coil galvanometer is more practical and moving magnet has become almost obsolete. Moving coil galvanometers are also of two types. One is suspended, the other type is pivoted type. We are first focusing on this suspended type galvanometer, but then before that, basic principle for both is a current carrying coil in magnetic field will experience a couple, and because of that it will get rotated. By studying that rotation, we could have the idea of current flowing through it. This is the basic principle of galvanometer. You see, the couple on the magnetic field is given by, on the current carrying coil is given by this relation NIAB sine theta. Theta is the angle between this area vector and magnetic field vector. Here one coil has been shown and the magnetic field has been produced with the help of two magnetic poles, north and south. When north and south have been exhibited here separately, doesn't mean they are existing separately. Might be like this, you see, it's a magnet, long magnet, and you have given this shape of this thing. So, a long magnet, this, suppose this is a straight line, which is not possible, I can't show like that. But then just suppose that this is a straight line and it's given shape of this thing. North and south have been shown closer. Doesn't mean that they are separate. It's two pole you are seeing here, two pole of a same magnet. Magnetic field is produced between them. If you take the poles of concave shape, then the angle between area vector and field vector is going to be always 90 degree, and in that case the sine 90 is going to be 1, and couple would be given by NIAB. This is the couple on the current carrying coil. Now focus over this. This is north, south, coil, metallic frame, and this suspension wire, and inside there is coil. We'll see what else is required within the coil for a greater sensitivity of the galvanometer right now. When the current passes through the coil, this coil will be rotated slightly, and when the coil gets rotated, the suspension wire will get twisted. Suppose the twisting is by phi, then the twisting couple produced will be given by C into phi. What is C? It's called torsional rigidity. Its value is given by this relation. R is radius, L is length, and eta, is known as modulus of rigidity. Torsional modulus or torsional rigidity here is C, and this is twisting moment. When the coil gets rotated by angle theta, the wire will also get twisted, and because of that twisting, there will be a couple, produced twisting couple. For the equilibrium, both must be equal. You see, NIAB, the deflecting couple because of the magnetic field and currents interaction, and this because of the twisting produced in the wire. Now, I equal to C upon NAB into phi. See, very interesting it is. You get I, K into phi, I proportional to phi. The deflection produced here is directly proportional to the current. We have replaced C upon NAB by K. Current sensitivity that is given deflection per unit current, and here it becomes 1 upon K. You want to increase the current sensitivity of galvanometer, you have to decrease the value of K. Obviously, we would like a galvanometer of greater current sensitivity, and for that we have to decrease the value of K. K has to be decreased, and K is given by, you see, C upon NAB. In place of C, you could write this thing 2L NAB. This is the value of K, that's known as reduction factor. K is known as reduction factor. You want a smaller value of K for increasing current sensitivity, and for a smaller value of K, you see, radius should be small. What does it mean? Wire should be thin. Length should be large. That means long and thin wire will be preferred for suspending the coil. N, A and B, these should also be greater for greater current sensitivity. Number of turns will be increased, area will be increased, and moreover, the magnetic field should also be greater within the two poles. In order to increase the magnetic field, what we prefer, we introduce some iron core within the coil. By doing that, you can increase the magnetic flux within the coil. And this suspension type galvanometer is prone to damages because of being a long and thin wire. It is most likely to be broken very easily. So, it's not portable, but at the same time, it's very, very sensitive and can measure the current even up to 10 to the power minus 9 ampere. In pivoted type, you see, second one, which is also known as Western type, the wire, suspension wire is divided, and we just pivot the coil between two pivots or nails, you might say. So, the possibility of getting broken is reduced. By doing that, portability has increased, but at the same time, in the same proportion, the sensitivity goes down. It could measure the current only up to 10 to the power minus 6 ampere. Despite all this, you see, when it comes to lab, for practical purposes, this becomes a more portable pivoted type, and this is most preferable instrument in our physics labs.